Hi students, welcome to my YouTube channel SADHIK-Physics. So in part 1 I already discussed about this alternating current and right about the dynamo and applications of alternating current across the resistor, inductor and capacitor, no, and we solved some few problems, no, related to this, no. So right, we'll do then like a second part, we'll apply alternating current across the combination of the devices in this part onto this, right. So let us if you did not watch first part, no, please watch it, and so that whatever the basics which I taught, no, it will be very helpful to understand the remaining parts now, right. So please watch part 1 and come back to this part 2. So let us go for this alternating currents, no. So part 2, right. So let us apply right alternating current across the RLC circuit. Let us take this one now, series RLC circuit, right. So in the series now, therefore there is a one resistor is there, no, this is one resistor, and there is an inductor is there, no, this is one inductor. So therefore, and this is one capacitor is there, and this we are going to connect one alternating current for all this one, right. So here what you are going to do, here E is equals to E naught, therefore sin of omega t. Now what will happen now, therefore some current it will be flown to this one now. So therefore this current, no, therefore how the current it will be there, I is equals to I naught into sin of omega t plus phi. Now I naught, how to calculate it now, I naught is nothing but a E naught by total resistance. Total resistance means like a not only a resistance, here reactance and all this one, no, total opposition by the this circuit, no, we will call it as like a impedance, Z we will call it as like a impedance, no, right. So here what you have to do now, you have to calculate this impedance and we have to calculate this phase difference, right. So how to solve such type of problems, no, let us see. First, what will be the potential difference across this one now? So we know the potential difference across this one VR. So the amount of current which is flowing I into R, clear. So potential, what will be the potential difference across this L now, right, I into XL. What will be the potential difference across the capacitor, VC is equals to I into XC. So will be the potential difference across this one now. So here we cannot add it of all this one now. Why? Because it is a sinusoidal function now, you have to take the phase into consideration now. So how to do such type of problems onto this one now, right. Here one very important concept I already discussed, so that is nothing but a phasor diagram. You have to draw the phasor diagram for this one. By using this phasor diagram we can solve this type of circuits is very easily. First let us see, first of all, current which is there, no, this current which is there, the same current will be flowing, same current will be flowing, same current will be flowing, clear. So as the same current is flowing across this one, no, therefore here we can rewrite it as like a, this is your current, right. So here current and this resistor, we already did this one now, phasor diagram, this is nothing but a VR, clear. So current, therefore VL, it is leading on to this one now, therefore it will be the VL, this is 90 degree. And what about VC now, therefore this it will be your VC, clear. So this it will be your phasor diagram now. Now what I can write it now, here, so VL and VC both are in opposite in phase, you remember that. So VL and VC both are in opposite in phase. What will be the phase difference between them now, 180 degree. So assume that VL is greater, therefore taken here now. What I can rewrite it as now, this is VL minus VC. So therefore here it will be the VR. So this is your current, clear. So now therefore what will be the angle between them now, therefore 90 degree. So that is your phase difference. This is your phase difference, I mean resultant voltage onto this one now. How you can write it now, like a parallelogram law, root of VR square plus VL minus VC whole square, clear. So in this way you can calculate the potential difference across this one now. How to calculate? V is equals to root of, so that is VR square plus VL minus VC whole square. This is your potential difference. In this way you have to calculate it. Now in this series circuit, no, what we know? We know that so current it will be the same. Current across this one it will be the same. So current I can write down current into resistance. Resistance means nothing but reactance. No, it will be equal to V is equals to VR is equals to I into R. I R whole square means I square R square. No, so here I into XL. Therefore I square taken common outside. So I into R square plus XL minus XC whole square. So this I and I get cancelled out. No, therefore I will get the impedance. Impedance is equals to, that is nothing but R square. Therefore XL minus XC whole square. This is your total impedance. Right? Total impedance in this circuit. Clear? Now we want to calculate the total impedance. I got this Z value. Right? So now what I want to calculate it now, again I should know what will be your phase difference. This is now. Clear? So this it will be your phase difference. Clear? How to calculate this phase difference now? Therefore here it will be the tan phi. So it will be can write it as like A. So this is our opposite side now. Therefore VL minus VC by therefore VR. R I can write down I into XL minus I into XC by I into R. So therefore it will be XL minus XC by, so this is R. R we can rewrite it as like a omega L minus 1 by omega C by R. R it will be equal to phi, it will be equal to tan inverse of therefore VL minus VC by VR. This is your phase difference. Very, very important. In this way we can calculate the phase difference. Understood? So we can calculate what will be the power factor inside this, in this one. No? So power factor, what you have tried it now? Power factor. So what is the power factor here now? So here you can rewrite it as, therefore here this is now, therefore here it is cos phi. What you will get it now? Cos phi. Cos phi means nothing but adjacent side by hypotenuse. No, therefore adjacent side is nothing but what? VR by root of VR square plus VL minus VC whole square. R I into XL both are same. No, R by root of R square plus XL minus XC whole square. R we can write down R by Z. This is your power factor. Very important. Clear? So in this way you can calculate the power factor. Power factor most important formula is R by Z. This is most important now. So power factor, so I got it as this phi. So what it will be your current now? Current you can write it as I naught, that is nothing but E naught by Z into sine of omega t. Phi is equals to tan inverse of VL minus VC by VR. Right? So these are the concepts now. Right? So which are involved with a series RLC circuit. Very important now. Why? Therefore if you want to do like RL circuit, only RL circuit or RC circuit or LC circuit, no, what do you do? If it is RL circuit is there, just delete this one. No, rest of everything the same thing. So where C is not there or XL is not there, VC is not there, that's all, you remove it. No, remaining thing it will be your answer. No, or if you want to write RC circuit, no, so you remove this L part, then you can continue the same part of this one. No, you can calculate it whatever the things. No, right? LC also, LC is applied with a source onto this one. No, also R you can remove it onto this. Right? So after calculating this power, right, power dissipated, no, what you can power factor, no, so power you can calculate it, no, power, what you can calculate, no, power, so that is nothing but a IRMS into ERMS into, so therefore cos phi. Therefore IRMS, you know it now, or I naught 1 by 2 I naught into this one, no, cos phi is nothing but a R by Z. You can calculate how much amount of power will be dissipated in this one now. Clear? Right? So this is power factor, and this is your phase difference, no. Suppose here L is greater onto this one, no, compared to this Vc, so therefore inductor is leading onto this one, no. There, suppose you can rewrite it as here, no. Suppose in this one, no, in this. So what you can write it now? If suppose here it is VL is greater than Vc or XL is greater than XC, therefore inductive circuit. Inductive circuit now. Therefore, here if it is VL is less than Vc, so therefore what you can get now? Capacitive circuit now. You understand? No? So when inductive circuit is there, therefore phase difference is nothing but a positive. So then afterwards it will becomes to the 0. Then afterwards phase difference it will become like a negative. So positive to negative it will be there onto this, right. That is also changes by frequency. Why? Because so omega L and 1 by omega C, 2 pi f into L by is equals to 1 by minus 1 by 2 pi f into C, right. So here if you really understand this one, no, so then rest of everything, no, you can calculate very easily. And in this one more part is there, no, like a resonance of your RLC circuit, no. So what is that resonance of your RLC circuit? So resonance in RLC circuit, now let us see. So resonance condition, right. What is this resonance condition? That means here resonance we already discussed in waves lesson, no. Therefore if it is incoming frequency and natural frequency are going to are both are same, no. Therefore that object is going to vibrate with a greater frequency onto this, right. So therefore here resonance will takes place onto this one, no. We'll see one very good application was there in this one, no. So right, most of the students they don't know, so try to learn this one, no. So here now let us see what is this at the resonance, no, maximum amount of energy transmission takes place now. That is nothing but a power will be maximum at this point. So power if it is want to be maximum, so at certain frequency we are changing, no, at certain frequency, resonating frequency we want to calculate. So at this point at certain frequency power is maximum. Power maximum means what? Should calculate like a current should be maximum. Current should be maximum. Current should be maximum means what? So Z should be minimum. Impedance should be minimum. When it will be the impedance will be minimum, Z is equals to, so the minimum condition. When it will be the minimum condition, so Z is equals to root of R square plus XL minus XC whole square. So when it will be the minimum now, the minimum condition is nothing but is equivalent to the R. When it will be possible now, when XL and XC, so both are equal now. XL is equals to XC. Or XL is nothing but what? Omega L is equals to 1 by omega C. Taken here now, omega square into 1 by LC, or omega is equals to 1 by root of LC. This is your angular frequency. So where resonance takes place now. Our frequency, resonating frequency. Resonating frequency. What is this resonating frequency now? So omega is equals to 2 pi f 1 by 2 pi into square root of LC now. This is your resonating frequency. At this frequency, therefore, the power will be maximum, or current will be maximum, or resistance will be, impedance will be minimum now. Or so reactance of inductor and reactance of our capacitor, it will be both are equal onto this. Clear? So F is equals to 1 by 2 pi into square root of LC now. Right? First of all, let us discuss this one now. Then afterwards, we will see what will be the application now. So if you really change the frequency, so how the current is going to change it now? The current or the maximum, the power, no? So the power will be maximum. When it will be maximum now, the power will be maximum. This is your frequency. That is omega. You can rewrite it as like a omega frequency. Right? So at this point, the power was maximum onto this, that is omega is equals to omega naught. So therefore power is going to get dropped now as you are going far away onto this. So we will take it as maximum power, it will be there at half of this one now, half of this deviation. After that is quickly it is going to fall onto this one now. So this range, this power range no, so we will be having maximum amount of power range. So this is having suppose certain amount of delta W, delta omega. So this side it will be there omega naught plus, so change in omega, therefore this side it will be there omega naught minus delta omega. So here from here to here, what you can call it now, this delta omega and delta omega, so this range, so this region, this 2 delta omega which is there, no, so this is nothing but a 2 into change in frequency, this is nothing but a, we can calculate R by L, so this we will call it as like a bandwidth. Bandwidth. What is this bandwidth? No? Let us discuss on to this one. No? Also, we can calculate the Q factor, no, or Q value. What is this Q factor for this circuit onto this one? No? Q value, Q factor. So this Q value will tell that how much amount of energy stored in the capacitor to how much amount of energy loss, or this Q value can be written as like a 2 pi into, so maximum energy stored per cycle by maximum energy loss per cycle, right. That means it should store more amount of energy and less amount of energy should be lost. If Q value is larger, that is said to be like a good, so resonating circuit onto this. Therefore, always a good circuit, if you want to calculate, no, you should have Q values will be large value should be taken. No. How to calculate this Q value? No, Q value can be calculated as, so very easy. So therefore, it is nothing but a omega naught into L divided by R we can write down 1 by omega C into R that is nothing but a, so you can write down therefore V L by V R, so V C by V R. So you can rewrite it as, so omega naught you can write it as 1 by square root of L C, so you can rewrite it as therefore, so 1 by R into 1 by square root of L C means root of L by C. So these are the formulas for the Q value. Clear? So very important now. Clear? So these are the concepts, so where, so maximum power it is going to take place now. Understood? No? Therefore, there is a one good application is there. So based on this one, no? Can you tell me where this RLC circuit we are going to use it? So this all the things, no, resonating frequency, bandwidth and all this one, no, where we will use it? In our day-to-day life, no, we are using this RLC circuit in most of the devices, no. So mostly it is used in the communication purpose, right. So simple thing, no, in our day-to-day life, no, you are using the TV and TV remote, no. So you are pressing the TV remote, therefore automatically there is a channel is changed in your TV. What is happening now? Do you get any time doubt? No. Therefore, if you press the TV remote, no, therefore how that channel is changing onto this, how that channel, how the TV is knowing that to display that channel only. Clear? So what is happening between the remote and TV and the channels which are there now? So this can be explained by using this concept. No, listen carefully. Suppose, so if you want to keep, or if you want to create one own TV channel or radio channel, now what you have to do, you should have one particular frequency range. That should be, you have to take the permission from the government, and you have to take one certain amount of frequency range. Some frequency range. Suppose I am taking one example onto this one. No? Suppose if you are taking like you are allotted with 100 megahertz to, so 200 megahertz. This was your frequency of your channel, if it is allotted for your channel. So 100 megahertz to 200 megahertz. This range is there, no? That is only we will call it as like a bandwidth. What is the bandwidth? No? This range of our frequency we will call it as bandwidth. Now what you have to do in your channel, so whatever you want to telecast your program, like a news or a song or anything, if you want to telecast in that program, no, therefore that all information should be telecasted with this frequency only. So we should not go for more than this one. Now we should not go for more than this. Why? Because some other channel will be having some other frequency range 200 to 300 like that. So therefore if you are apart from this one, if you are telecasting, no, so that it will be mixed with a other channel, no, that interference will take place, no, further propagation it will not take place. So you have to you are allotted this frequency range, you have to telecast your information from this range only. So you are telecasting, okay, therefore you are telecasting in all the directions, no, by the through the antenna and all satellites onto this one, no, so you are telecasting. Therefore for anyone of you are watching the your channel, no, therefore right, somebody watching the TV, so for the TV some hundreds of channels is coming now. So therefore what you are doing now, therefore you are pressing some number onto this on the remote. So you are changing the frequency of the TV. That how you are changing the frequency of the TV? By changing the capacitance which is fixed in your TV. So when the capacitance is changed, frequency will be changed. Therefore the frequency of the TV will change. So that frequency of the TV may be matched with one of the channel with the same frequency. Therefore at that point, therefore the resonance will take place, no, therefore that channel only will be played in the TV onto this. Clear? So therefore if you are setting the frequency of this range of your TV, so therefore that channel only will be get displaced because of due to the resonance takes place onto this. Clear? Right? So in this way, whenever you are pressing the remote onto this one, no, therefore you are changing the frequency of your TV and you are setting the frequency of that the incoming channel, no. Therefore some hundreds of channels will be having their own frequency. That frequency is matched with the frequency of your TV. Resonance takes place, it will display the only that channel. Some other channels are there, no, that is there is no resonance will take place, no, that channels will not be displayed on your TV onto this, right. In this much things will be there. So in that which circuit it is used, no, RLC circuit only it is used in your TV. Not only the TV, therefore even radio, you are tuning the radio. Therefore tuning the radio means what? The frequency of the radio and frequency of the the radio channels, no, is matching onto this. Therefore that type of channel only was displayed onto this. Clear? So therefore this RLC circuit is mostly used in the communication purpose, no, and most important is the resonating condition and resonating frequency. So is only the most important point. Clear? So in this way you can understand about this resonance of your RLC circuit now. Clear? Very important now. So this is your RLC circuit now. In this way you have to calculate the impedance now, and this is your right, this is your phasor diagram, very important. So in phasor diagram, you remember that now, in any phasor diagram is there, no. So phasor diagram, this is your phasor diagram is there. So therefore you can understand. So therefore here, therefore you can take it as this is your suppose V. So therefore your vertical component, no, whatever the vertical components are there, no, these vertical components will give us like a V sin phi. So will give us like a instantaneous values. Right. So along this direction, no, along there is a current is there, this is a current, no. So therefore you can write down I sin phi, like that it will be there. So these all are your instantaneous values. So along this direction, no, therefore there is no power dissipated, no, therefore power is not dissipated, no, therefore that type of currents are nothing but a wattless current. Wattless current. What is this wattless current? No, wattless current is nothing but a where power dissipated, it will be the zero. That means the power, I mean the current which is flowing through the capacitor and inductor, no, that are nothing but a power is not there onto this, or power dissipation it will not be there. That type of current is there, no, that type of currents are said to be like a wattless current. How to calculate the wattless current? No, I is equals to, therefore there I naught, whatever this wattless current is there, this is your wattless current, no. So I RMS into sin phi, or I naught into sin phi if you want to calculate. So peak value, RMS value, anything. So this is your wattless current onto this. What is phi now? Phi is nothing but this one, no, that is nothing but a phase difference. Clear? So this is about your wattless current, no. Clear? Now we will see some different questions onto this one, no. Very simple, right? So let us see. And also one more important point is there. So here in RLC circuit, okay, suppose in RLC circuit, no, right, RLC series circuit. So what will be the impedance now? Impedance is nothing but a R square plus XL means nothing but a omega L minus 1 by omega C whole square. R we can write it as R square plus therefore 2 pi FL minus 1 by 2 pi FC whole square. So you can draw the graph between, so therefore Z and frequency. What will happen now? Therefore, as the frequency is lower now, therefore this it will become like a maximum onto this. So then it will comes to the down onto this. Then it will comes to here. So then afterwards again it will be going to increase. So this is your where impedance is minimum, that is nothing but a resistance here now. So this is the frequency is nothing but a resonating frequency. So this is the variation of our impedance with a frequency in the RLC circuit. One of your the important graph for this. Clear? Now let us see different questions, no. So and some problems, no, we can do it on. Let us see one question on to this one, no. Right, here there is an RLC circuit is given, right, it is a variable frequency, frequency is variable, right. So here the resistance is given 40 ohms, these all are connected in series. So inductance is nothing but a 5 Henry, capacitance is nothing but a 80 microfarad, no. So this is now, therefore the frequency is changing, so the frequency is not constant. So when the frequency is changing, we have to calculate what at a resonating frequency. What is the resonating frequency? Or we can calculate omega R. What is omega R? Therefore 1 by square root of LC. How much will get it now? 1 by root. Root L is how much now? 5. C is how much now? 80 into 10 to the power of minus 6. So root, right? 8 is nothing but 8 5 40, 40 is nothing but 400. 400 means 1 by root of 4 into 10 to the power of minus 4. That is nothing but so 1 by 2 into 10 to the power of minus 2. So taken here no 100 by 2, that is nothing but 50 radians per second. So therefore omega naught, therefore it is nothing but 50 radians per second. This is your omega naught. This is your angular frequency onto this. Clear? So now we may calculate at this resonating frequency what is the impedance. Very important point, no. Impedance is nothing but what a Z. See, at resonating frequency, immediately you should get into your mind, at resonating frequency, impedance is nothing but a resistance. Impedance is nothing but a resistance. Why? So impedance, what is the formula here now? Root of, therefore R square plus XL minus XC whole square. What did I say? This one both are equal, no? So therefore impedance will be nothing but a resistance at this point. So if any other frequency is there, it is not resonating frequency at that point, therefore impedance will not be equal to R. So therefore here impedance is how much, no? Therefore 40 ohms. Clear? So we want to calculate RMS current here now. What is RMS current here now? Third one. Therefore IRMS. What is IRMS now? So therefore ERMS by impedance. What is ERMS now? 230. So therefore here and 230 divided by. So let us take this is 200 volts. So that for easy calculation, no. So 200 volts. 200 easy calculation. So let us see here, no. Therefore here it will be how much now? 200 divided by 40. So get cancelled out now. Therefore it will be nothing but a 5 ampere. This is your RMS current. Right? So then we want to calculate. So what will be the voltage drop, RMS potential drop across the resistance now. That means what is this one now? What is this now? So he is asking that. So at this point, therefore VR is asking, therefore it will be VL and therefore it will be the VC. So we want to calculate it. RMS potential drops across this one now. How to do it now? Very simple one now. Therefore, so we got it as VR VR is nothing but a IRMS into R. How much now? IRMS is nothing but a 5 into 40, therefore it is nothing but a 200 volts. This is a 200 volts. So therefore VL, how much now? IRMS into XL. Yes, sir? So first of all, XL is nothing but a omega L into IRMS. Omega is how much now? We got it as nothing but a 50. L is how much now? L is nothing but a 5 Henry. Omega is nothing but a 50. So L is, we got it. Okay. Then what you can write it now? So here omega, therefore it is 5 into also current is also nothing but a 5. How much now? Therefore 25, therefore 125. So 1250 volts. Clear? So what will be the VC now? VC, so therefore IRMS into XC. What is XC now? Therefore IRMS into XC is nothing but a omega into C. IRMS is nothing but a 5. Omega is nothing but a 50 into C is how much now? 80 microfarad. 80 into 10 to the power of minus 6. Therefore here it will be the 10. So 1 by 8. So this is 10 to the power of 4. So 10 to the power minus 4. This is 10 to the power of 4. Right? So 10 to the power of 4. What you can write it now? Also, right? 10,000 divided by 8. Therefore 2 4s are 5,000. 2 2s are therefore 2,500. So 1250. Therefore 1250 volts. Clear? Potential drops across the capacitor, potential drop across the inductor, both are same. But how, why we are taking RMS voltage is nothing but right here. What will be the total net voltage here now? Net voltage it will be nothing but 200 volts. Why? Because it is nothing but a VR square plus so VL minus VC whole square. VL minus VC both are same now, 0. Therefore it is VR is nothing but a resultant onto this one now, that is nothing but we got it as 200 volts. That's why here across this one now, here it is 200 volts. Clear? Now what will be the power dissipated? What is the power dissipated across this one now? Power. How to calculate the power now? See, one more important point. So therefore what will be the power factor onto this? So we know power factor now, cos phi, it is nothing but a R by Z. Z is also is nothing but a R. Therefore at resonating frequency, power factor will be equal to, that is nothing but a 1. Clear? So why? So Z is also nothing but a R. So we'll cancel now, power factor will be 1 now. So what will be the power now? Power is nothing but a IRMS into ERMS into 1. Therefore cos phi. IRMS is nothing but how much now? 5 into ERMS is nothing but a 200. So into 1. Therefore here 10. Therefore it will be the 1000 watt. Clear? In this way you can calculate, right, about RLC circuit. All this one now, like different combinations now, you can calculate what are the things now. But here this is a question for resonating frequency question now. If suppose any other frequency it is given now, at that point resonating is not taken place now, at that point impedance will not be equal to R. So you can calculate the impedance by using this formula. And current also it will be the different. So these all the things now it will becomes like a different values. So but right, you should understand so how to solve it now. So right, so at resonance no, these are the conditions onto this. Clear? So sometimes they may ask you what is the Q factor also. So Q factor, what is the formula here now? Q value 1 by R into square root of L by C. So this also you can use it, even you can calculate this Q value also. Clear? So these are the maximum possible questions now, you may expect it for the examination now, right? Now let us see one more different concept now, or we will do like a one problem and we will do like a concept onto this, like we will apply alternating current across the two combinations RL, RC, LC like that. Clear? So let us see, first of all we will see RL circuit. So across the resistor, no, therefore here this resistor and inductor. We will do like a problem and concept, no, therefore here. So let us take this is your R is nothing but 100 ohms and L is nothing but suppose 0.5 Henry, not hertz, Henry. Now applied for voltage is nothing 240 volts and 50 hertz. So what are the things now you have to calculate it now? First of all you have to calculate the what will be your IRMS. How to do it now? Here L is not there, RLC circuit only, therefore same thing. So first of all you have to calculate impedance. What is the impedance now? Therefore R square plus XL minus XC. XC was not there, therefore XL whole square. Clear? So root of R square plus XL. XL is nothing but omega L whole square. Substitute, you know, omega you can write it as like a 2 pi into F, or here also you can rewrite it as like a, therefore it will be 2 pi into F into L whole square. Clear? So here it will be the 100, so 100 whole square plus 2 pi into 50 into L is how much now? 1 by 2 whole square. Clear? So how much it will be now? Therefore here it will be the 1 by 2, or we can write it as like a 1 by, or we can write it as this L value, easy calculation, no? Therefore we can write it as like a 1 by pi Henry. So it is easy, so that you can rewrite it as 1 by pi whole square. Pi get cancel out, no? Therefore root of 100 square plus 100 square. How much it will be now? 100 means 100 root 2 will be your impedance onto this. Now what will be the IRMS now? IRMS is nothing but ERMS by impedance. What is your ERMS now? This is your ERMS value. Therefore 240 divided by 100 into root 2, these two get cancelled out, no? Therefore here 2.4 divided by root 2 R. So you can simplify, so just mathematical simplification, no? So this is your IRMS. Clear? Here anything can be calculated, no? So again, so what will be the VR? That is nothing but IR. So therefore VL, that is nothing but I into XL. Like that you can do it any question onto this one. Clear? Okay. So let us do VL. VL is nothing but I into XL. I into 2 pi into F into L. I is how much now? Therefore here it will be 2.4 by root 2 into 2 pi into frequency is nothing but 50 into 1 by pi. Get cancel out now. This is 100. So 100 means into multiply this one now 240 divided by root 2 volts. Like that. So RMS potential drop across this one now. So what will be your these type of questions, no, they may ask you what will be your phase difference. Phase difference, how it will be there now? Tan phi. Tan phi is nothing but a, so VL by VR. Yes or no? VL is nothing but a R XL by R. XL is how much now? XL we can rewrite it as like a, so 2 pi F into L divided by R. So this will become like a 1. 1 means, so phi it will be equal to, right, tan inverse of 1. When it will be there now? So 45 degree, right? So phi it will be equal to 45 degree. Clear? So tan 45 it will be equal to 1. Therefore phi it will be equal to 45 degree. 45 means how much now? So pi by 4. Clear? Right? So what will they may ask you, what is the time lag onto this one now? Therefore here it will be t by 2 pi into, so pi by 4. So get cancel out now. Therefore t by 8. T is how much now? T is, it is a 50 hertz is given. 50 hertz. So what you can write it now? Therefore 1 by 8 into 1 by 50. How much now? 5 is a 40, 400 seconds. Time lag, phase difference. So they may ask you any questions onto this one. So here also one more question you can add it here. So what is that now? Let us see how therefore the frequency and the impedance is changing here now. So the graph for impedance and frequency. If the frequency is 0, right? If the frequency is 0, therefore here impedance, what is the formula here? Impedance is nothing but a root of r square plus 2 pi f into L whole square. If the frequency is 0, the impedance will be equal to r. Then as frequency increases, impedance also will be increases. Therefore here the impedance and frequency graph can be drawn like this. Right. So in this way you can solve any type of concepts, no, even power dissipated also you can rewrite it as no power dissipated. What is the power dissipated? No, power factor also you can rewrite it as no. What is the power factor here now? Power factor. What is the power factor now? So cos phi is a power factor, cos 45. So that is nothing but 1 by root 2. What will be the power dissipated here now? Power dissipated is nothing but IRMS into ERMS into cos phi. IRMS we know it now, ERMS by Z. Clear? Right? What is your current? Current we discussed, no? So we discussed current here now. IRMS current, no? 2.4 by root 2. Right? So it will be 2.4 by root 2 into 240 into therefore 1 by root 2. So therefore it will be 1. So 2.4 into 240 divided by 2. Therefore it will be 1.2. So that is nothing but a 12 into 24. So how much it will be now? Right? So here 24, 12. So how much now? 8, 4. Therefore 24, 288 watt. Like this you can calculate power dissipated, right? All these questions, right? So you can calculate it. So in this way, I think more than these questions now you may not expect it about the RL combination now, right? So now let us see here RC combination now we are going to discuss now, right? So first let us go for this is your RC combination now. R is equals to 100 ohms. So capacitance, so if you want to calculate 1 by omega c, so right, C is also nothing but a 1 by pi microfarad, right? So here voltage is nothing but a 200 volts and 50 hertz. So here all this one now again the same thing. So if you want, this is your RMS voltage, we want to calculate current now. Current means compulsory you have to calculate impedance. What is the impedance now? Therefore root of R square plus XC whole square. First let us see XC. XC is nothing but 1 by omega c, 1 by 2 pi FC. So 1 by 2 pi F is how much now? 50 by 1 by pi into 10 to the power of minus 6. Get cancel out, no? 100. So 100 means 10 to the power of minus 4, 10 to the power of 4. So how much it will be now? Root of, therefore here 100 whole square plus XC is nothing but a 10 to the power of 4 whole square. It's a very huge. Clear? So therefore here you can write it as 10 to the power of 4. So 10 to the power of 4 taken out now, 10 to the power of 2 root of 1 plus 10 to the power of 4 it will be there. So therefore nearly So 10 to the power of 4 whole square. So nearly here also 10 to the power of 4 it is taken out, no, therefore 1 plus, so 10 to the power of 4 it will be there, therefore 10,000. Okay, how much it will be now, therefore 10,000. So 1 2 3 4. Okay, 10,000 only, 10,000 means 10 to the power of 4. Nearly you can write down 10 to the power of 4, so will be your impedance onto this, right? Clear? Now what will be your current now? Current IRMS, no, that is nothing but a ERMS divided by impedance. ERMS is how much now? 200 divided by, so impedance is nothing but 10 to the power of 4, 2 into 10 to the power of minus 4, minus 2, so that means 0.02 ampere. So this is your current, right? So current is very low, therefore here we can rewrite it as, again we can calculate VR is nothing but a IR, or VC is nothing but a I into XC, like that you can calculate it now, correct? So we want to calculate, let us see, VC, I is how much now? 2 into 10 to the power of minus 2 into XC is nothing but a 10 to the power of 4. How much it will be now? 200 volts. Clear? Now let us see again. So what will be your phase difference now, that all this no. So what will be your phasor diagram now? This is your current now, so this is your voltage VC. Clear? So this is nothing but a VR, so this is your resultant now. So this is your phase difference, therefore tan phi it will be equal to minus, so VC by VR, that is nothing but a minus XC by, therefore R, minus, therefore XC is how much now? 10 to the power of 4 divided by 100, so minus 100, right? I don't know this value, so phi is equals to tan inverse of minus 100, right? So this is your phase difference, no, we don't know the value of this. Clear? So phase difference you can calculate it like this, and path difference, time difference also you can calculate it, no. What are the things, we calculated, no, right? So here one more new question, no, we can calculate it, no. What is that? How the variation of the, right? So impedance and frequency. So how it will be there? Therefore here impedance is equals to root of R square plus XC means 1 by 2 pi FC whole square. If F is equals to 0, F is equals to 0 means 1 by 0 is infinity, 1 by infinity it will be there. So as F it is goes to infinity, this will becomes to the 0, comes to the R, that means it is infinity, so therefore it will be comes to here R like this, finally it will become like a R. In this way, therefore the variation of our impedance with the frequency in RC circuit, no, is possible on this. Clear? Right? We'll do one more application now, that is LC circuit, no, with a alternating voltage. Now let us see here, there is a one inductor is there, no, therefore one capacitor is there, so it is connected with a one, suppose it is 200 volts and 50 hertz. So L is equals to 1 by pi Henry, so C is equals to 1 by pi, therefore microfarad, suppose. Now what will happen now? Let us see. So here first of all let us calculate the impedance, no. So what is the impedance here now? Resistance is not there, so root of R is not there, no, therefore XL minus XC whole square, root get cancelled out, no, impedance will be equal to XL minus XC. So XL is nothing but a, so therefore 2 pi F into L minus 2 pi F into C, right? Let us calculate what is your XL and XC. So 2 pi F into L, 2 pi into 50 into 1 by pi, get cancelled out, no, 100 ohms. So XC it will be equal to how much now? So therefore 1 by 2 pi 50 into 1 by pi into 10 to the power of minus 6. So get cancelled out, no, 100 10 to the power of 4 here. So here XC is more, therefore more dominating one onto this one, no? Therefore you can rewrite it as like a xc minus xl, clear? So xc minus xl, so this is nothing but 10 to the power of 4 minus 100, so 10,000 minus this one, no? This is nearly equal to 10 to the power of 4, clear? So let us see here now, we will change it this one, no? Microfarad to millifarad, let us see. So that what will change here, no? Millifarad. Millifarad means what will happen now? So 10 to the power of minus 3. So therefore here 100, therefore it will be the 10. So it will become like a 10 ohms. So here dominating one was what? Therefore here XL minus XC. So dominating one was 100 now, therefore 100 minus 10. So therefore 90 ohms will be your impedance. So what will be your IRMS now? Right? IRMS is nothing but a ERMS divided by impedance. How much it will be? Therefore 200 divided by 90. This will get cancelled out, no? 20 by 9 ampere. Clear? So here also we can rewrite it as like a VL I into XL and VC is equals to I into XC. Like this we can calculate it now. Even peak values also we can calculate. Amplitude of this voltage means V naught we have to calculate it, no? So RMS voltages means RMS current only we have to use it, no? Like that. Clear? So now what it will be the phase difference now? Phase difference however between these two, it will be like a 180 degree onto this. So phase difference, it will be nothing but a pi. So that implies, therefore what it will be a time difference here now? Cos, right? So time difference, let us see now. What is the time difference now? So delta t is nothing but t by 2 pi into pi get cancelled out, no? Therefore t by 2. Clear? So if you want to calculate t by 2, therefore t by 2 is nothing but a 50. So 1 by 2 into 1 by 50. So is nothing but a 1 by 100 seconds. Clear? This is your time difference now. So what will be your power factor now? Therefore cos pi. So cos 180 it will be equal to, therefore minus 1, right? So like this you can able to calculate it, no? About this, right? Now let us see here, no? Okay, this is your okay, one more important, no? Here how the frequency is changing the impedance here now. Therefore impedance it will be equal to 2 pi f into L minus 1 by 2 pi f into C. So therefore the graph between, therefore impedance and frequency, so how much it will be now? Therefore here frequency is 0 here, no? So this is 0 means infinity. So it is infinity, therefore it is comes to here, no? Then afterwards it goes to here. Therefore here it will be your resonating frequency. Clear? Huh? So in this way, therefore there is a impedance and frequency, it is going to change it, right? So in this way you can calculate the problems related to this one, no? Right? So this is about our alternating currents, no? So most of the times, no, more than this you may not expect any questions onto this one, no? So right? So go through it thoroughly, right? So please subscribe to my channel, no? Thank you for watching now, right? If time permits, no, in any time, no, therefore if any difficulty questions are there, so I'll try to solve that type of questions, no, so that you can able to get more clarity onto this. But minimum basic things, no, compulsory, this you need to require. Thank you.